Thyristor commutation techniques. What is meant by thyristor commutation? The process of turning off a SCR is known as commutation of a SCR. Turning off means bringing the device from forward conduction state to forward blocking state. A thyristor is turned on by applying a signal to its gate cathode circuit. For the purpose of power control or power conditioning, a conducting thyristor must be turned off as desired. Once thyristor starts conduction, gate loses control over the device. Therefore, external means may have to be adopted to commutate the thyristor. There are several commutation techniques have been developed to reduce the turn-off time of the SCR. The main requirement of main commutation requirements are: first one, the anode current of SCR must fall below the holding current. Second requirement is that a reverse voltage is applied to thyristor for a sufficient time to enable it to recover to blocking state. These are the two requirements for commutation. There are several commutation techniques are there. These different commutation techniques are natural commutation or line commutation and forced commutation. Natural commutation is also known as line commutation. This type of commutation can occur only when the converter circuit is fed from a AC source. That is in natural commutation. The main requirement of commutation is the anode current must be below the holding current. Anode current flowing through the thyristor must fall below the holding current, and second condition is that there should be a reverse voltage across the thyristor. So in natural commutation is usually employed in an AC circuit, and main significant of a main advantage of using an AC circuit is, in an AC circuit the input is a sinusoidal voltage. So a sinusoidal voltage has a natural zero pose condition. So in natural commutation, the commutation happens when the input voltage is 0, and after 0 pose the voltage across the thyristor goes to negative naturally, because our input also goes to negative voltage. So this type of commutation is known as natural commutation. In natural commutation, the thyristor is subjected to a negative voltage naturally due to the presence of the input AC signal. Usually this natural commutation is employed only in a AC circuit. Examples are a rectifier circuit. Rectifier circuit is a AC to DC converter circuit and a AC voltage controller circuit. The commutation happens naturally in natural commutation circuit. Okay. Example for a natural commutation circuit is a rectifier circuit. The figure shows a half-wave rectifier circuit with a resistive load. Our input voltage Vs is equal to Vm sin omega t. That is an AC input. Vm is the maximum of input voltage. This is our sinusoidal voltage. We are turning on the SCR at omega t equal to 0 instant. Our firing angle is equal to 0 degree. So at omega t equal to 0 instant, we will turn on our SCR. Then SCR starts conduction. Therefore, output voltage V0, or voltage across the resistance, is equal to input voltage up to pi. At omega t equal to pi instant, the input voltage is equal to 0. At omega t equal to pi instant, the input voltage is equal to 0. After omega t equal to pi, there is a negative input voltage coming across the thyristor. Due to this negative voltage, the thyristor goes to its blocking state, as well as the current also is equal to current flowing through the thyristor also is equal to 0 at omega t equal to 5. Thus the thyristor turns off. So voltage across the thyristor is equal to source voltage. Okay, voltage across the thyristor is equal to source voltage. That means in this half wave rectifier circuit, commutation happens naturally. So this type of commutation is known as natural commutation. Okay, next one is the forced commutation. Next type of commutation is the forced commutation. In forced commutation, we are employing external commutation circuit to turn off our SCR. That is, we are using some external commutation circuit to bring the anode current below holding current, as well as to employ a negative voltage across the anode cathode terminal of a thyristor. We are employing an external circuit to obtain the commutation requirements. Depending upon the type of external circuits used in a forced commutation method, there are different types of forced commutation: resonant pulse forced commutation, complementary forced commutation, impulse forced commutation, load commutation, and external pulse commutation. In all these commutation techniques, we are employing a external circuitry to turn off our circuit. Okay, but in the case of natural commutation, we are not employing any external circuitry to turn off our SCR. The SCRs naturally turn off due to the input AC signal. Okay, usually this forced commutation is employed where our supply source is a DC source. For example, a chopper circuit. A chopper is a circuit which is used to convert fixed DC into variable DC. Also in the inverter circuit. In the inverter circuit, inverter is a circuit which is used to convert DC input to AC output. In these two condition, our input is a DC source. Therefore, the input has no zero voltage source or zero current source. So for turning off a SCR, we should have to provide an external commutation circuitry. That type of commutation is known as, or turn off method of a SCR is known as forced commutation. To turn off a thyristor, the forward anode current should be brought to 0 for sufficient time to allow the removal of charge carriers. In case of DC circuit, the forward current should be forced to 0 by means of some external circuit. This process is known as forced commutation. With DC supply, we use external circuit and active passive components to reduce anode current's values below holding current. The circuit involved in this process is known as commutation circuit. The components used in this circuit is known as commutating components. Okay, forced commutation is usually employed in DC choppers and inverter circuit where the input supply is a DC supply. Okay, next is the comparison between forced commutation and natural commutation. Natural commutation requires AC voltage. Forced commutation our source is a DC voltage. In natural commutation, there is no external circuitry or external components are not there. But in forced commutation, external components or external circuitry is needed. This natural commutation is used in rectifiers and AC voltage controller, where we are using AC as our input voltage. The forced commutation is employed in DC choppers and inverters. In natural commutation, SCR turns off due to negative supply voltage. Forced commutation, SCR turns off due to current and voltage both. Fifth point is there is no power loss take place. No power loss take place during the commutation process in natural commutation, but in forced commutation we are employing external circuitry for commutation, so there is power loss. Natural commutation cost is 0. Forced commutation there is significant cost because we are employing external circuitry for commutation. This is the comparison between natural commutation and forced commutation. Next is a load commutation circuit. In load commutation circuit, there is an inductance and capacitance. The inductance and capacitance is known as commutating component. This inductance and capacitance is the commutating component. Here in this example, R is our load. In first circuit, the commutating components L and C are connected in series, and in second circuit, the capacitor is connected in parallel with the load and inductance is connected in series with the resistive load. These are the two type of circuit combinations. Either we can connect L and C in series with the resistive load, or we can connect C in parallel with the resistive load and L in series with the resistive load. In both cases, the overall circuit must be under damped system. Okay. Usually for low value of resistance load, L and C are connected in series. For high value of resistance, L and C are connected in series, connected in parallel. Okay. When these circuits are energized from DC, here VS is our DC source. When these circuits are energized from DC, current waveforms are shown like this. This is the current waveform. These circuits are under damped circuits. So first the current increases and reaches a maximum, then it starts decaying, and at current zero position, pose, and there is a current zero pose. At that current zero pose, thyristor commutation happens. Load commutation is employed in thyristor circuit supplied from a DC source. The nature of the circuit should be such that when energized from a DC source, current must have a natural tendency to decay to zero for the load commutation to occur in a thyristor circuit. That is, first the current rises to a maximum value, then it reaches to a zero position. At this zero position, or at this instant A, thyristor commutation happens. The load commutation is also known as Class A commutation, Class A commutation, resonant commutation, or self-commutation. A practical circuit employing this load commutation is a series inverter. Series inverter is an example for employing this load commutation technique. Okay, this is about load commutation. Load commutation is also known as Class A commutation, resonant commutation, or self-commutation. In this, we are connecting a commutating component L and C in such a way that our entire system response is like a under-damped system. In under-damped system, first the current rises, then it decreases and it reaches to a zero value. At the zero position, our commutation happens. Okay, this is about thyristor commutation techniques. Thyristor commutation is broadly classified into natural commutation and forced commutation. Natural commutation is employed in AC circuit. Forced commutation is employed in DC circuit. In forced commutation, we are employing external circuit to obtain this commutation, but in natural commutation, naturally the thyristor goes to its turn off condition. Okay, thank you.